What we've been doing is looking at heat and temperature and made a little homemade thermometer and then did an experiment to investigate thermal capacity. Adelle, I understand you are at the coalface, if you like, of caring and looking after marine animals. Would you like to tell us a little bit about yourself and the job that you do?
Hi, Steve. My name's Adelle, and I'm the curator here at the Marine Study Centre. And yeah, my role is to ensure that the animals are well and healthy, and that they're living in suitable environments, which of course the temperature plays a huge part or a huge role in those environments.
You're using water straight out of Otago Harbour, is that right?
Mostly, Steve. We have two different systems here. We have flow-through systems and we have some closed systems, semi-closed systems. So when I refer to a flow-through or an open system, that water is being pumped directly from the harbour up through some filtration systems, and then it flows via gravity back through our tank and straight back out into the harbour again. So the temperature of that water is completely and utterly reliant on what temperature of the harbour is at the time. The closed systems give us a little bit more control over the temperature of the water, but they do pose a lot of other potential problems. It means that we have a huge range in temperatures, right from down to 3-4 degrees occasionally in the winter time, up to over 20 degrees in the summertime. So that's a massive range for our animals to be able to cope with and deal with. And our selection of our animals that we choose is very reliant on being able to survive within that range of temperature. So the harbour itself acts like a great big heat exchanger. It's a pretty shallow harbour, and at low tide, 1/3 of the harbour is exposed as sand flats. So those sand flats absorb heat. In the summer months, when you've got days of hot temperatures, especially days consecutively, that temperature can rise a couple of degrees several days in a row. So that's huge changes that the animals have to deal with and cope with.
Okay, so you're saying that because you're taking harbour water and it's changing with a wider range than just open ocean water, because you've got more rapid rise in temperature in summer of the landmass, and the water's shallower, and the ocean water comes in and gets heated by that, as you said, as you call it, a heat exchanger, but then it loses more heat energy in winter to the atmosphere as it's cooling. So therefore, as the water comes in over winter, it loses more heat to the ground that's been exposed as well. So,
absolutely, Steve.
So
the coastal water, so off the coast of Otago, that water is pretty constant. Once you get down below sort of 20 metres, it's sitting at 13 to 15 degrees, and that doesn't change much right throughout the year.
Okay, so this sounds like it's about thermal capacity, like the huge mass of the open ocean water has a more stable temperature and doesn't heat up as much as a shallow, less massive harbour water. Is that right? So
that's absolutely right.
So let's take that to your closed system, which is a much smaller volume. So what are the issues with the closed system with temperature there?
Well, exactly the same situation, Steve. The smaller your tank, the more vulnerable you are to increases and decreases in temperature in your tank. So the larger your tank system, the easier it is to maintain your temperature. The tanks that I've got behind me here are for seahorses and pipefish, and they're on a closed system. But they are really vulnerable to other factors that are affecting them, like the light that's coming from the windows behind. For our animals is that we don't want rapid changes of temperature. So those harbour temperatures, we're talking about extremes of 2 or 3 degrees over the period of a day. But if you've got your little fish tank sitting in a hot room or in a cold room and you light the fire that's right beside your fish tank, that temperature can increase by 2 or 3 degrees in a matter of half an hour, and it's those rapid temperature shocks that are really hard on the animals.
Can I just share my screen here, Adelle?
Yeah, please.
So you're talking that this is the harbour temperature, and we could get up to 16, 17 degrees here in summer. This is January, February. Drop down to between, around about 7 degrees here. This is interesting in that the orange is a 10-year period from 2006 to 2015. So what we're getting now is around the 7 to 8 through winter time here, and then rises again into the summer here, November, December. But this is a change of over, as you're saying, a long period of time, months and months and months and months and months. But you're saying that the shock would be that if in your tank you had one of these changes here, a 2 or 3 degree change, which here has occurred over 3 or 4 weeks, happening in a day or two, and that would be your problem in a closed system.
Absolutely. So it affects the animals in all sorts of different ways, Steve. You have the initial shock, obviously, of that temperature change, which most animals can deal with, 2 or 3 degrees, but anything more than that really, really stresses them. And that stress, if it's happening constantly, affects their immune systems drastically. So then they're more prone to parasites and bacterial infections and things like that. So it might not kill them straight away, but the lifespan of your animals will be substantially lessened through those temperature shock events.
So how do you monitor and manage this?
So where you're looking at now is behind the tanks, the seahorse tanks that we were just looking at the front of before. And you can see a whole lot of paraphernalia here. We've got filter systems that have got pumps combined in them that circulate water around the system. But we also have our chillers. Okay, so this allows us to help regulate the temperature. Now they are just chillers, so they only cool the water. In Otago here we have cold temperate water, so we'll look a little bit about how much that changes through summer and winter. But our biggest problem is the water getting too hot in the summer and that causing stress for the animals. So when that temperature increases, the animals' metabolism increases. They use a lot more oxygen, and we have to remember as well that cold water holds more oxygen. So as that water increases, the ability, or the temperature of the water increases, the ability of it to hold oxygen decreases, but the fish are using more oxygen because their metabolism has increased. So it's a bit of a double-edged sword. So we have to be able to control the temperature and ensure that there's enough oxygen in the water for them to be able to breathe and carry on with their daily routines.
So Adelle, if in summer these tanks stay warm for a length of time, isn't evaporation going to affect salinity as well in the tanks?
Absolutely. So the temperature has an effect on all sorts of things. It's going to affect your salinity, it's going to affect your pH, it's going to affect the turbidity of your water. It will affect the amount of toxins that are in the water.
When you transport animals from the field into the laboratory or take animals from the aquarium out to other centres for teaching, you've got the problem of transporting these animals and keeping temperature at a suitable condition for their well-being. Can you tell us a little bit about that? I see you're in this very fancy, colourful, what do we call it? An aquavan, is that it?
We are, Steve. So this is the first aquavan ever been made in New Zealand. The biggest thing about this van is that it's got a controlled temperature. So we're able to regulate the temperature of the animals when we collect them from within the field or transport them around to different places. Come on in for a look. So what we've got here is a view of the life support system. We've got things like a generator providing power to keep all the equipment going. You've got an air blower, so it's putting oxygen into the water. But behind me here, we've got a heat exchanger. I'm going to turn it on. And you can see the numbers all changing on the front dial here, and it's telling me that it's 9.4 degrees. Okay, there's no water in the system today, so that's actually measuring our air temperature. this is pretty cool because this heat exchanger not only cools the water, but it can heat it as well. So you can see all the little metal plates here give the heat exchanger a huge surface area to be able to transfer heat. To be able to control the temperatures in our tanks for the animals, we have to get rid of heat out of the system. And you can see that there's ventilation everywhere, from on the doors to extractor fans to vents in the roofs. The tanks are made of plastic. Plastic is a really good insulator, so that allows us also to keep the temperature of the water much more regular. We don't lose the heat in and out of the tanks as quickly as if we've made them out of a product like metal. It's pretty stressful being collected from the wild and taken from where you're used to living. So if we can minimise those other stress factors like temperature, it gives the animals a much better chance of survival and doing well when they get back to the laboratory environment. Here's some of our open water tables and our cup tanks, and you can see some of the animals that can walk back in the aqua band. The biggest influence on water temperature is exchange of heat through light and the sun. So these tanks here are really, really affected by the sunlight that comes into the room. It wasn't ideally built. We've got some great skylights above us here. And so we can counteract that by having quite high flow through.
Now, the tank you're at now, Adelle, and the tank that you started with the seahorses, people watching can actually link into a webcam for those, can't they?
They absolutely can. So you can look at how the animals are moving and in time. You can watch them being fed. That we discussed to start with. This open tank that we've got here is an open system. It's got that water running straight from the harbour through it. And then the seahorse tank, which is also on the webcam, is a closed system. And one really neat thing to look for, especially in these tanks in the summertime, and it's something we haven't talked about today, is algal growth. And so that increases huge amounts in the summertime. And so the workload for our aquarists increases also.
Hey, this has been fantastic, Adelle. It's amazing how critical temperature is to the whole understanding of the marine world, but also management of marine systems in both an educational and research context. Thanks very much.
You're welcome.
We have with us here Rob Lewis, who is, well, tell us about yourself, Rob.
I am currently working at the New Zealand Marine Study Centre. I have been for the last 3 years or so, along with Steve here. And before that, I was a postgraduate student with the Marine department in Otago University. And I've been studying sharks as part of my master's for the last few years doing that. Prior to that, I worked in South Africa for a small while, working mostly with great whites over there for about 3 or 4 years. So yeah, I'm kind of just into the whole sharky world of things.
How does the world of the shark have to deal with differences in temperature over the planet, and how does that end up what does that end up looking from a point of view of a shark scientist such as yourself?
Right, so temperature in terms of shark science is pretty important. So this is an image in the background here you should be able to see of sort of ocean temperatures around the world. In the middle here you've got these equatorial regions, and those are the bits that are basically closest to the sun. Orange and red are the warmest, and then going into the green and blue where it gets colder, and then right up to the top where it's purple, that's your very cold polar regions, right? So yeah, in these equatorial regions, all this water here is being heated by the sun the most, and this heat is then eventually dispersed throughout the entire ocean using ocean currents. So in these equatorial regions, this is what we like to call our tropical areas. And the tropical areas for sharks are probably the most populated in terms of species numbers. And most sharks are what we call poikilotherms. Now, a poikilotherm is essentially what we call cold-blooded, right? So animals that have their metabolism, their digestion, even their respiration and things, they're all impacted by the environmental temperature around the animal
So even if we say cold-blooded, they're not actually cold-blooded if they're in warm environment. They take on, their body has the temperature of the environment they're in. So if they're in warm water, they're warm. If they're in cold water, they're cold.
Yeah, that's right. That's exactly right. In the tropical regions, you're usually looking at above 20 degrees, so between 20 and 30 degrees. Very nice, very warm, fantastic for functions of sharks.
Hold on, mate, Rob. That's in degrees centigrade?
That is in degrees centigrade. I hope no one's using Fahrenheit, but that's where you find most of your sharks, because it's easier for sharks to be in that kind of temperature. But sharks have been around for a very long time, and quite a few species have started to make use of the colder waters as well. They don't want to have to compete with all the other species in the tropical areas. So you get fewer species, but still quite a lot living in what we call temperate waters, and that's the green and the blue on the maps.
Right. And Rob, if I'm right, there's been recent interest in a shark that's very tolerant of very cold waters. Is that right?
Yeah. So the shark that you're probably thinking about is what's called the Greenland shark.
Wow, look at that.
So these guys actually live in what are the polar regions, so the purple parts of the map from before. So these guys, as you can see, they're pretty hearty looking, loads of scratches and things going on. These guys function at base metabolic rate. Their maximum speed, cruising speed for swimming is about 2.4 kilometers an hour. So putting that in human terms, the average person walks at about 5 kilometers an hour.
So this is a slow walk.
Now, this is a very slow shark, but these guys live in waters that are exceptionally cold, and there are about 3 species that really make use of these very cold waters. And they've got some very, this is slightly above freezing, so 0 to about 12 degrees is what we're talking here, centigrade. And of course, not many animals can make use of these sorts of water temperatures. So these guys pretty much have free reign in the environment they have as one of the top predators around there. They can grow exceptionally large, even though they grow very slowly. So they can grow close to maximum sizes of between 6 and 7 meters. And they grow at about 1 centimeter a year when they start reaching their adulthood. So you can imagine that it's a very long trip to get to those maximum sizes. Everything's slower. Yep, everything's slower. So the metabolism's slower, the heartbeats are slower, muscle function is slower, everything degrades slower in those temperatures as well. And so that's why this animal, particularly, research has shown that they've got lifespans between 300 and 500 years. Their bodies have adapted quite specially to these to the cold water temperatures. Normally, most sharks have got a very large liver, and in their liver they've got this oil called squalene. And squalene is, one, how they store their energy, because they don't really have fat in their body. But secondly, it's a huge part of how they maintain buoyancy. These sharks can't have that oil, because that oil will actually freeze in the water that they're living in. And so they've actually made use of this thing called trimethylene oxide, which is all throughout their body, this compound. And that prevents their blood from freezing. It prevents their muscles from basically freezing and exploding.
I was just to say, Rob, that the chemical name you gave just sounded like an antifreeze.
Yeah, but it's exactly what it is. It's an antifreeze, and it's a natural antifreeze that these animals have come up with, and it prevents the blood from freezing under both temperature and pressure. So yeah, pretty cool little adaptation that these animals have.
They're pretty restricted to that area, but there are sharks that are quite migratory and they move. How does temperature relate to those large migrations and movements that we see in some shark species?
Right, so I mean, the biggest migrations that we usually see are in sharks that live in what are the temperate waters. So this is your 12 degrees to about 21 degrees centigrade range. Things like your great whites, the mako sharks, seven-gill sharks. These are all animals that tend to prefer waters that change quite considerably between the seasons, right? And so as those changes occur, these sharks have to move north or south or to different areas of the world to try and find the correct water temperature that's best for them.
Is it that to do with food or reproduction, or something else? What's
A little bit of column A, a little bit of column B, Steve. So a lot of the food that these sharks rely on. So I mean, I've only mentioned the big sharks here, but obviously there are a lot of smaller sharks, spiny dogfish and rig, small things that also rely on eating things that don't like the cold water as much either. So certain prey species will move with temperature fluctuations, which will impact the sharks, but the sharks themselves will do it as well for their own body functions as well. So yeah, the prey moves, the sharks move for the prey and for their own body function. And then reproduction is another reason that it can happen. But we most often see it with a winter-summer cycle, where as the water starts heating up, that's when we start seeing reproduction occur, or that's when we start seeing the numbers increase in close coastal areas as those shallow parts are getting warmer. That there are special cases of some sharks that are homeotherms, so those are animals that maintain their own body temperature on the inside.
like us?
What was that, sorry? Yeah, like us, yeah, exactly.
So ours is what, 37 and a half, something like that.
Yeah, yeah. So with these animals particularly, they don't have a set temperature per se, but they do have the ability to maintain a higher temperature than the surrounding environment around them. And that is done by using a strip of red muscle down the center of the shark's body, which is basically the main pistons that push the shark's tail. So these muscles are constantly working, they're constantly generating heat, and there is a very fine mesh net of veins and arteries around these muscles that absorb the heat from the red muscle creating, using the energy and creating the heat, and then distributing that via the blood to the other parts of the body to maintain a warmer overall internal temperature than the outside. So it's a very clever bit of evolution that's gone on, really. Great whites, mako sharks, porbeagle sharks, and salmon sharks are the ones that are known to be able to maintain their temperature higher than the surrounding water temperature. And again, the salmon sharks and the porbeagles particularly can be quite high in latitudes, both sides of the world.
So when you say high in latitude, they're into those blue-purple areas where it's...
Yeah. So making use, and essentially they've got a little bit more control, so they can go into those very cold areas and generate a bit more body heat themselves so they can still function.
Because they're generating it from the stored chemical energy, and then that gets transferred into the blood, which mostly water can pick up that heat energy and carry it somewhere else.
Yep.
And am I right, the ones that you've mentioned are quite large? They've got quite a large body mass? Yeah.
So that's got another aspect of temperature, of course, is this thing called Glycantrothermy, or larger masses retaining heat for longer times. So large animals tend to retain heat better than small animals, leatherback turtles and those large walruses and things like that. That's why they're so good at regulating their temperatures, because they're big animals. Smaller sharks, they've got a lot more trouble with maintaining temperature and making sure that they have to stay in the right temperature zones that they decide to live in. So yeah, the ones that I've mentioned are all very large species, and even the Greenland shark, and the sleeper shark, which is another species very similar to the Greenland shark. These guys are 6-7 meters in size to try and help keep those temperatures stable.
Right. So this is a little bit to do with thermal heat generation and thermal capacity. So like the mass means you've got more heat storage there happening. But also,
exactly, yep.
You've got a surface area to volume ratio thing going on. As they get bigger, their volume increases by the cube, whereas surface area by the square. So therefore, a larger organism is going to have less heat loss and gain through the surface, and more heat retention in their volume.
Exactly. And that's a perfect explanation of gigantothermy, basically. The bigger you are, the better you're going to be at storing that heat. Some recent research by some scientists here at Otago, Rosa Edwards is her name. She's been doing work with seven-gill sharks down on Stewart Island, and there again she found that we're seeing quite a large change from season to season between that summer and winter time, and it's all dependent on that temperature as to where we're seeing sharks and how many of those sharks we're seeing at a time.
And Rob, you run the Shark Spy program at the New Zealand Marine Studies Centre, and
Yes.
students were keen to get involved more into sharks. You'd be the guy to communicate with. Can you tell us a little bit about the Shark Spy program and what goes on there?
Yeah, sure. So Shark Spy is essentially trying to gather sightings and shark information from the wider community. And we're also working with local schools to go out and actively survey and try and find sharks using underwater videos. So if you did want to check out what Shark Spy is doing, feel free to go. We've either got a Facebook page you can go have a look at. So just go to Facebook and search Shark Spy Otago, and we should pop up. Or if you want to go check out some of the cool shark sightings we've actually reported, go to iNaturalist.org, I want to say. Just search iNaturalist in Google, and then once you're an iNaturalist, search for Shark Spy, and you'll get to see all the sightings and things that we've reported. If you have sightings yourself, you can also report them to either of these locations as well. And we're doing this to try and gather incidental information. There's a lot of information that goes missing, and there's a lot of knowledge in local communities about their own water spaces that we're trying to tap into using this project.
Oh, fantastic, Rob. It's been great talking to you. Okay, hey, thanks very much, Rob. Enjoy the rest of the day, and I'd be keeping clear of that friend of yours from Iceland behind you. He's got the eye on you.
Don't worry, I can walk twice as fast as he can swim, so I think I'm all right.